In question 10, it says that the diagram shows the curve y is equals to x square cos 2x. The curve has a maximum point at m where x is equals to p. We have to show that p satisfies the equation p is equals to half tan inverse of 1 upon p. Now, as it is a maximum point, we know that that means dy dx is equals to 0. So in the first step, we'll find dy by dx. And as two terms are multiplying, we'll use product rule. So we'll say u is equals to x square and u dash will be is equals to 2x. V is equals to cos of 2x. So v dash will be, so derivative of cos is minus sine and 2x derivative is 2. So minus 2 sine of 2x. So we'll write it as uv dash, or sorry, vu dash, that will become 2x cos of 2x plus, and this is a minus sign, so we can just write minus over here, and this will become minus x squared 2. So this is 2 over here and sine of 2x. And we'll put it equals to 0. Now, solving it, we'll bring 2x square sine 2x on the left hand side. So we'll have 2x square sine of 2x is equals to 2x cos of 2x. And now, as we have to satisfy the equation p, or we can say basically p represents x over here. So this 2 and 2 will cancel out. And we have x remaining over here as an x square over here. So x square and x will cancel out. And we can write it as, so we have to bring tan. So sine x upon cos 2x, that will become tan 2x. And we can bring this x on this side. So this will become 1 upon x. Now, as we have to find x, so this will become tan x is equals to 1 upon x. So if we take tan inverse over here, so this will become x is equals to tan inverse of 1 upon x. But there is 1 upon 2 over here as well. We have x is equals to p, so that's fine. So let's check if we have missed out on any value over here, because there's supposed to be a 1 upon 2 over here. So this is 2x, vu dash is 2x cos 2x, and uv dash is minus 2x square sine 2x. Okay, yeah, this is tan 2x over here. So this is sine 2x upon cos 2x will be a tan 2x. In place of x, now we can write p as well. So we can now write it as 2p is equals to tan inverse of 1 upon p. And then finally, p will be is equals to 1 upon 2 tan inverse of 1 upon p. Now in part 2, it says use the iterative formula to determine the value of p correct to 2 decimal place, give the result of each iteration to 4 decimal place. Now for this, we always need the initial value of p. So the initial value of p, we know that the value of p lies between 0 and 1 upon 4 pi. So we can start off by taking any value between 0 and 1 upon 4 pi. So 1 upon 4 pi is 3 3.142 upon 4. So this is more than 0.5. We can take any value. We can start off with 0.5 over here. So we can start off with the initial value 0.5, and we'll write it as, so the first value of p will become 1 upon 2 tan inverse of 1 upon 0.5, which is tan inverse of 2. Now substituting this in the calculator over here, we'll get, okay, so tan inverse of 2, and then we'll divide by 2. Okay, so shift tan inverse of 2, and we have to make sure that our calculator is in radian mode. Okay, so shift tan inverse of 2, that is 1.11, and then we'll divide our answer by 2, so we'll get 0.55. So this will become 0.55, and we have to give our answer to 4 decimal place, so that is 55357. So this will become 0.5536. I will substitute this value to get the next value. So this will become 1 upon 2 tan inverse of 1 upon 0.5536. Now substituting this in the calculator, shift tan inverse of 1 upon 0.5536. Okay. And then dividing this answer by 2, we'll get 0.5325. So this will become 0.5325. Now substituting this again into the equation, we'll get the third value. So 1 upon 2 tan inverse of 1 upon 0.5325. So shift tan inverse of 1 upon 0.5325. And then we'll divide this answer by 2 again. We'll get 0.5407. And we'll have to do it a couple of more times. And our final answer will be somewhere around 0.4. We have to give a final answer of P to 2 decimal place. We can do it one more time. And if our answer is still coming to 0.54, we can give a final answer of P as 0.54. In the next part, we have to find, showing all necessary working, the exact area of the region bounded by the curve and the x-axis. So the total area will have to integrate the equation, which is x square cos of 2x. And the limits are pi upon 4 and 0. Now to integrate this, we'll have to use integration by parts. And we know that the formula for integration by parts u dv is vu minus v du. So we'll apply the late formula over here where we have algebraic and trigonometric terms. So the algebraic term will be taken as u, which is equals to x square. So du will become 2x. dv will be taken as cos of 2x. The integral of cos 2x is sine 2x, and then we'll also divide this by 2. Now we'll just simply substitute this into the formula. We will get vu, which is x square sine 2x upon 2 minus, so this will become 2x. We can keep the 2 outside, and this will become x v du. So okay. So v du will become vu and then v du. So that is 2 over here, x and then sine 2x upon 2. So this 2 and 2 will cancel out, and we can now simply substitute, or we can simply integrate x sine 2x one more time using integration by parts. Again over here, u will be x, so du will become equals to 1. dv will be sine of 2x, and the integral of sine 2x is minus cos 2x and then upon 2. So now applying integration by parts over here, we'll get vu again. So vu will become minus x cos 2x upon 2 minus v du. So v is minus cos 2x, so we can make this a plus cos 2x upon 2 and then dx. Integrating cos 2x, we know that becomes sin x. So this is minus x cos of 2x upon 2. Integral of cos is sine, so this will become plus sine 2x. And then we divide by 2 again, so this will become a 4. We have a minus sign outside, and this remains as it is. Now simplifying this, we'll get x square sine 2x upon 2 plus x cos 2x upon 2 plus sine 2x upon 4. Now we have to simply substitute the upper and lower limits. The upper limit was pi upon 4. So substituting x is equals to pi upon 4 over here, we can do this separately. So sine 2 into pi by 4, that is sine of pi by 2, or sine 90, and we know that sine 90 is 1. And so sine 90 will become 1, and x square, so x is pi upon 4. So this will become pi square upon 16 into 1 upon 2 plus pi upon 4. Cos 2x will become, again, when we write x is equals to pi upon 4, that will become cos pi by 2, which is 0. So this whole term will become a 0. So we don't have to write it down. And then sine 2x is 1. So this will become plus 1 upon 4. Minus, Now substituting 0 over here, so this will be 0, this term will be 0, and this term will be 0 as well. So our final answer will be pi square upon 32 plus 1 upon 4. That should be the final answer. And if we take the LCM as 32, so this will become pi square plus uh, this will multiply by 8, so 8 upon 32. There is there's just one correction over here. This minus and this plus should have become a minus over here, and these are the small mistakes that we have to be very careful about. So this should have become a minus 1 upon 4. So pi square, this will be pi square minus 1 upon 4, and we can write it also as pi square minus 8 upon 32. And this will be our final answer for the area of the region bounded by the curve and the x-axis. In question 1, it says solve the equation ln of x squared plus 1 equals to 1 plus 2 ln of x, giving your answer correct to three significant figures. Now, in the first step, we'll first write 1 also in terms of ln of x. So we can write it as ln of, so this will become ln of x squared plus 1 is equals to, we know that ln of e is 1, so we can write it as ln of e plus ln of, and we can bring the 2 over here and make it a power of x. Now, as they are multiplying, as they are adding over here, so we can write it as ln of x squared plus 1 is equals to ln of e multiplied by x squared. So that will become ln of ex squared. And then we can just equate both the sides. So we will get x squared plus 1 is equals to e x squared. Now, e is like a constant. So to solve this equation, we can write it as ex squared minus x squared is equals to 1. So ex squared minus x squared divided by 1, we can write it as, if we take common, x squared is equals to 1. So that will become e minus 1. So we can write it as e minus 1 is equals to 1. So x squared will be is equals to 1 upon e minus 1. And finally, to find the value of x, we'll write it as square root of 1 upon e minus 1. Substituting this in the calculator, square root of 1 upon e minus 1, we'll get one answer that will be 0.763, and the other answer will be a negative as it is a square root, so we'll ignore the other value, and this will be a final answer. In question 2, we have to solve the inequality x minus 3 is less than 3x minus 4. Now, as there's a modular sign involved, we can first whole square both the sides. So we'll get x minus 3 whole squared is less than 3x minus 4. Expanding, we'll get x square minus 6x plus 9 is less than, and this will become 9x square minus 24x plus 16. Now simplifying, we'll bring the left hand side on the right hand side. So this will become 8x square minus 24 plus 6, that becomes minus 18x, and 16 minus 9, that will become a plus 7 is greater than 0. Now factorizing it, we'll get 8x square minus 14x minus 4x plus 7 is greater than 0. And taking 2x common, we'll get 4x minus 7. And taking 1 common, we'll again get 4x minus 7 is greater than 0. So our values will be 2x minus 1 and 4x minus 7 is, so this is greater than 0. Now using a quadratic curve to understand how to give this as an inequality, we will write this as, so x will be 7 upon 4 and x is 1 upon 2. And it is greater than 0, so we need values which are above the x-axis. So what we will think is that the answer will be x is greater than 7 upon 4 and x should be less than 1 upon 2. However, there's one thing we'll have to be very careful about, and that is that from this equation, what we know is that this modulus sign means that this x minus 3 is always positive, which means that 3x minus 4 is always greater than 0, as it is a modulus sign, which means that this value is always positive, and if it is less than 3x minus 4, it means that 3x minus 4 should also be greater than 0, which means that the value of x that we will be getting should be at least be greater than 4 upon 3. Now, as x is less than 1 upon 2 does not lie in this domain, so our only answer in this case should be x is greater than 7 upon 4. In question 3, in the first part, it says express the equation cot theta minus 2 tan is equals to sine 2 theta in the form cos 4 plus cos square plus c, where a, b, and c are constants to be determined. Now, in the first step, in place of cot theta, we can write it as cos upon sine, and we can write 2 tan as 2 into sine upon cos, and we can also write sine 2 theta as 2 sine cos. So these identities, they are provided to us in the formula sheet as well. Now taking the LCM, we'll get cos square minus 2 sine square upon sine cos is equals to 2 sine cos. Cross multiplying, we'll get cos square minus 2 sine square is equals to 2 sine square cos square. Now in place of sine square, we can write it as 1 minus cos square. So now simplifying this, we'll get cos square minus 2 plus 2 cos square is equals to 2 cos square. And okay, so this is not sine square. This should have been 1 minus cos square. In place of sine square, we are writing 1 minus cos square. So this will become 2 cos square minus 2 cos to the power of 4. Bringing the right hand side on the left hand side, we'll get 2 cos 4. So this is plus 3 cos square. This will become minus 2 cos square minus 2 is equals to 0. So our final answer will become 2 cos 4 plus cos square minus 2 is equals to 0. So the values of a, b, and c will become 2, 1, and minus 2. In part 2, it says, hence solve the equation for theta between 90 and 180. Now we already have the equation for this term, so that is 2 cos 4. So we'll get 2 cos 4 plus cos square minus 2 is equals to 0. Now we can write this as a quadratic equation, and we can substitute this in the calculator. So let's say we can write it as x is equals to cos square. We will get 2x square plus x minus 2 equals to 0. We can solve the quadratic equation using the quadratic formula, and we can also substitute this in the calculator, but it is necessary to show the working. So this will become b square, which is 1 square minus 2 into 2 into minus 2, b square minus 4ac upon 2a. So 2 times 2 will become 4. So x will be is equals to now substituting all of this in the calculator, we can simplify this further, and at test, this will become 1 plus, so this is 2 to the 4, 4 to the, okay, sorry. So this is a small mistake over here. This is b square minus 4 ac. So a is AC. So A is 2 and C is also 2. So 2 into minus 2. So this will become 1 plus 4 times 2 is 8. 8 times 2 is 16. And so this will become square root of 17 upon 4. Now substituting this in the calculator, the two values of x that we'll get will be x is equals to, so that will be 0.78, and x will be is equals to negative 1.28. Now substituting in place of x, so we have cos square of x is equals to, one of the values is 0.78, and one of the values is cos square of x is equals to minus 1.28. Now as it we cannot have the square root of a negative value, so this will cancel out. We can write it as, so that theta will be, so we can in place of x, well, that's the same as theta, so we can say theta will be cos inverse of square root of 0.78. Substituting this in the calculator, so shift cos inverse of square root of 0.78, that gives us 27.97. So the basic angle will become 27.97. And as we only have to take values between 90 and 180, so let's first make this in the quadrant. So this will be A, C, T, and S. Now the square root shows that we can have the values of cos in all the quadrants, positive and the negative ones. But as the domain is only between 90 to 180, so we'll just make the basic angle over here. So this angle will be 27.97, and our value of theta will become 180 minus 27.97. So 180 minus 27.97, that is equals to 152.03. and we can write our answer in degrees to one decimal place as 152.0, which will be our only answer. In question 4, the parametric equation of the curve are given and we have to express dy by dx in terms of t. Now in the first step, we'll find dx by dt. So that will be is equals to 2t, and dy by dt, that will be is equals to, so derivative of 4t will become 4 plus derivative of ln of 2t minus 1 will become, so 2t minus 1 will come in the denominator and the derivative will come in the numerator. Now to find dy by dx, we will divide dy by dt by dx by dt. So this will be 4 plus 2 upon 2t minus 1 and divided by 2t. Taking the LCM, we'll get, so 4 times 2t, that is 80 minus 4 plus 2 divided by 2t minus 1, and we can write it as multiplied by 1 upon 2t. So simplifying, we'll get 8t minus 2 divided by 2t minus 1 multiplied by 2t. So this will be the dy by dx. And we can just leave it like this, or uh, multiply in the denominator. It doesn't matter. We'll still get the full marks. Now, once we have the dy by dx, in part 2, it says find the equation of the normal to the curve at the point where t is equals to 1. Now, at the point where t is equals to 1, so we already have dy by dx, which gives us the gradient of the tangent. Now, dy by dx is 8t minus 2 divided by, so this is 2t minus 1 into 2t. So substituting t is equals to 1, we'll get 8 minus 2 upon 2 minus 1 into 2 into 1. So this will become 6 upon 1 times 2. So the gradient will become 3. Now dy dx gives us the gradient of the tangent. So the gradient of the normal will be is equals to minus 1 upon 3. And to find the equation, we also need the x and y coordinates. So in this equation, x is equals to t square plus 1. We will write t is equals to 1. So x will be is equals to 2. And y is equals to 40 plus ln of 2t minus 1. So 40 plus ln of 2t minus 1. So 2 minus 1, ln of 1 is 0. So y will be is equals to 4. And now we can write a final equation as y minus y1 is equals to m into x minus x1, which is 2. Now we can simplify it and write it as 3y minus 12 is equals to minus x plus 2. And then as we have to give our form equation in the form ax plus by plus c, so we'll bring everything on the left hand side and we'll get 3y plus x minus 12 minus 2 is equals to 0. So the final equation will be x plus 3y minus 14 is equals to 0. In question 5, it says in a certain chemical process, a substance A reacts with and reduces a substance B. The masses of A and B at time t at the start of the process are x and y. It is given that dy by dt and x is equals to 10 upon 1 plus t squared. At the beginning of the process, y is equals to 100. We have to form a differential equation in y and t and solve this differential equation. Now, as we need a differential equation in y and t, so in the first step, what we'll do is in place of x, so dy by dt will be is equals to minus 0.2. In place of x, we'll write 10 upon 1 plus t. So this will be whole squared and multiplied by y. Now, we'll bring y on one side and dt on the other side. So we can write this as dy upon y is equals to, so 10 into 0 minus 0.2, that becomes minus 2 upon 1 plus t whole squared, and dt will come on this side. Now integrating both the sides, so dy upon y, the integral of 1 upon y, that becomes ln of y, and to integrate minus 2 upon 1 plus t squared, we can write it as minus 2 into 1 plus t to the power of minus 2. Increasing the power by 1, we'll get minus 2 into 1 plus t power minus 1 divided by the new power, which is minus 1. So minus minus cancels and we'll get minus 2 upon 1 plus t. So we'll get ln y is equals to minus minus cancels. So this will be 2 upon 1 plus t plus c. Now to find the value of C, we know that it says at the beginning, which means t is equals to 0, y is equals to 100. So we write it as ln of 100 is equals to 2 upon 1 plus 0 plus c, or c will be is equals to ln of 100 minus 2. And then finally, we can write our final equation as ln of y is equals to 2 upon 1 plus t plus ln of 100 minus 2. And we can give this in many different forms. One of the other forms could be we can make y our subject. It did not ask us to give our equation in terms of y, but if we give our equation in terms of y, that will be equals to, so y will be equals to e to the power of, we'll write this whole thing, that is 2 upon 1 plus t plus ln of 100 minus 2, and we can simplify it even further, but even this will give us full marks. In part 2, it says find the exact value approached by the mass of B as T becomes large. State what happens to the mass of A as T becomes large. Now we know that Y represents, and we know it, Y represents the mass of B and X represents the mass of A. So we know that ln Y is equals to, ln Y is equals to 2 upon 1 plus T and plus ln 100 minus 2. Now, as this t value becomes really large, so 2 upon a very large value is approximately equal to 0. So we can say ln y is equals to ln of 100 minus 2. We can bring the 2 on the left hand side and write it as ln of 100 minus ln of y. This will become ln of 100 upon y is equals to 2. Now, uh, solving this equation, we'll write it as e to the power 2 is equals to 100 upon y, or y is equals to 100 upon e squared. So as the value of t becomes very large, the mass of b, which is y, is equals to 100 upon e squared. And we know that x is equals to, from the equation given above, 10 upon 1 plus t whole squared. And x is basically the mass of A. So x is equals to 10 upon 1 plus t's whole squared. Now again, as t becomes really large, when we divide 10 by a very large value, that is approximately equal to 0. So we'll say that the mass of A becomes 0 as t becomes very large. In question number 6, it says that the complex number 2 minus iota is denoted by u. It is given that u is a root of the equation where constants a and b are real. We have to find the values of a and b. Now, if the complex number 2 minus iota, which is represented by u, is a root, so in place of x, we can write this value 2 minus iota. So if you write 2 minus iota whole cube plus a into 2 minus iota whole square minus 3 into 2 minus iota plus b is equals to 0. Now, what we know about this, what about the root of a complex number is that if one of the roots is 2 minus iota, then the other root will be 2 plus iota. So we can also substitute 2 plus iota to make the second equation, and then we can solve these two equations simultaneously. So first, expanding this 2 minus iota whole cube, we can first write it as, we can first do 2 minus iota whole square on the side. So 2 minus iota whole square will become 4 plus 4 minus 4 iota plus iota square. Now we know that iota square is minus 1. So 4 minus 1 will become 3 minus 4 iota. So to find 2 minus iota whole cube, we can write it as 3 minus 4 iota and then multiplied again by 2 minus iota plus a into, we know the expansion of 2 minus iota whole square is 3 minus 4 iota. This will become minus 6 plus 3 iota plus b is equals to 0. Expanding this, we'll get 6 minus 3 iota minus 8 iota plus 4 iota square plus 3a minus 4a iota minus 6 plus 3i plus b equals to 0. Simplifying, we'll have 6 minus 3i minus 8i, which will become minus 11i. So we can just write minus 11i over here. We know that I square is -1, so this will become -4 plus 3a minus 4ai minus 6 plus 3i plus b equals to 0. In -11 plus 3 will become -8. We can simplify this equation now. 6 and -6 will cancel out. So the term we'll have it -11 plus 3 iota is -8 iota. We can take the 4 on the other side, and on the left hand side we'll have -8i plus 3a minus 4ai plus b, and we can write it as is equals to +4. Now to find the values of a and b, we can just compare both the sides. So let's put the real terms on one side, 3a plus b, and the complex term, and we can just take iota common. So we can write it as plus. So this will become, and okay, so iota is common, so we'll write it as plus iota, and in the bracket we'll have -8 minus 4a is equals to 4. Now on the right hand side we have a real term 4, and we don't have a complex term, so we can write it as 0i. So now if we compare, we'll get 3a plus b is equals to 4, and -8 minus 4a is equals to 0. So 4a will be is equals to -8, and a will be is equals to -2. Once we have the value of a as -2, we can write it over here. 3 into -2 plus b is equals to 4. So b will be is equals to, this will become 4, and this is -6, so that will become a +6. And the value of b is equals to +10. So the values of a and b will be, uh, a will be -2 and b will be +10. In part 2, it says, on a sketch of an argand diagram, shade the region whose points represent complex number z, satisfying both the inequalities z minus u modulus is less than 1 and z less than z plus iota, z is less than z plus iota. Now, what we should know is that what this actually means is that the distance of z from this complex number u is less than 1. So we already know what u is, and that is 2 minus iota. So 2 minus iota will be, so let's say this is 1, this is +2, and -1 is over here. So this is where the point is. This is where the complex number u is, and z is at a distance which is within 1 cm of this. So we'll make a circle of radius 1 centimeter. Okay, and let's try and make it a bit more accurately. So if we make a circle of radius 1 centimeter, this is what it will look like. And we know that this point will be 3, this point will be 1, and this point will be -2. And it also says that z is less than z plus iota. Now, to make this, what we know is that the distance of z from the origin, because we don't write z minus 0, but this actually means that the distance of z from the origin and the distance of z from plus iota. So we'll write it as, we can write it as minus iota to understand it better. So the distance of z from the point -1. So the distance of z from the point -1 is lesser. So first we'll make a perpendicular bisector. So this line will be passing exactly in between these 2 points. So we have the 2 coordinates. One of them is origin 0 and one of them is -1. And this, the complex number z is closer to this point. So it means we'll have to shade the region which is above the line but within the circle. So the region that we'll shade is this one. Again, if we have z minus u is less than 1, it means that the distance of z from the point u is within 1 centimeter. So first we make a circle of radius 1 centimeter, and then what this means is that the distance of z from the point origin is lesser than the distance of z from the point -1. Using the concept of vectors, when we write it as we say ab, that means b minus a, or we are going from a to b. So when it says z minus origin, so it means from z to the origin. So z must be somewhere above this line as the distance is lesser. from the distance of z from this point. In question 7, it says prove that if y is equals to 1 upon cos theta, then dy by d theta is equals to sec theta tan theta. Now, if y is 1 upon cos theta, we can write it as y is equals to cos to the cos theta, cos minus 1 power theta. When we find dy by d theta, we can first also write it as cos theta to the power of minus 1. And then when we differentiate, we multiply minus 1 over here. And then we write cos theta as it is. We decrease the power by 1 and also write the derivative of cos theta, which is minus sine theta. So minus minus will cancel out and we'll have sine theta upon cos square theta. We can write this as sine theta divided by cos theta multiplied by cos theta. We know that sine theta upon cos theta is tan theta. So we can now write dy by d theta as tan theta, and 1 upon cos theta is sec theta. So this will become tan theta sec theta. In part 2, it says prove the identity 1 plus sine theta upon 1 minus sine theta is as given. Now, if you have to prove this as what is given on the right hand side, to simplify this, we can start off by just multiplying the numerator and denominator with the conjugate of the denominator. So what this actually means is we can write it as 1 plus sine, and we can multiply the numerator by 1 plus sine and the denominator by 1 plus sine as well. So expanding the numerator, we'll get 1 plus 2 sine plus sine square theta, and divided by this will become 1 minus sine square theta. Now 1 minus sine square theta is cos square. So we'll have 1 plus 2 sine theta plus sine square upon cos square. Now we can divide each of the terms by cos square and write it as 1 upon cos square theta plus 2 sine theta upon cos square theta, or we can write it as cos theta into cos theta, and then plus sine square upon cos square theta. So 1 upon cos square, that will become, so that should become sec square theta, plus this will become sine theta upon cos theta is tan theta, and 1 upon cos theta is sec theta as we did earlier. So this will become 2 sec theta and tan theta, and this will become plus 1. But in the question, we have 2 sec square theta instead of sec square theta and minus 1 over here. So in place of 1, maybe we can use an identity. So the identity we can use for 1 could be, oh, sorry, a mistake. Sine square upon cos square is tan theta, tan square theta. So this will become tan square theta. And now we know that the identity for tan theta is, so sec square theta is tan square theta 1 minus tan square theta. 1 plus tan square theta. So that is tan square theta plus 1. So tan square will be sec square minus 1. So when we write sec square theta minus 1 over here, so we'll get sec square plus sec square, that will become 2 sec square theta. We already had 2 sec theta tan theta and minus 1. Now we have the identity that we had to prove. And now in the next part, it says, hence find the exact value of the integral of 1 plus sine upon 1 minus sine. Now we can use the identity over here, which is 2 sec square theta. So we have 2 sec square theta plus 2 sec theta tan theta minus 1. So we can write this in place of 1 plus sine upon 1 minus sine. And we have the limits pi upon 4 and 0. And now we have to integrate it. Now we know that the integral of sec square is tan theta. So in place, when we integrate sec square theta, we'll get 2 tan theta over here For 2 sec theta tan theta in part 1, what we learned was that the derivative of 1 upon cos theta is sec theta tan theta. Okay, so we can write it over here that the derivative of 1 upon cos theta was, let me just check it out again. The exact answer was tan theta sec theta. So keeping 2 as constant, the integral of tan theta sec theta should become 1 upon cos theta, and integral of -1 should become theta. So now we have the integral, which is 2 tan theta plus 2 upon cos theta minus theta. And now we can just substitute the limits. The first limit is pi upon 4. So tan pi upon 4, that is equals to 1. So this will become 2 plus 2 upon cos of pi upon 4 is 1 upon root 2. So we can write it as 1 upon root 2 minus, and this will be pi upon 4. And then we substitute the lower limit, which is 0. So this will be 2 tan 0 is 0 plus cos 0 is 1. So this will become plus 2 minus 0. Now we know that this is 2 minus plus minus 2. This, so 2 and 2 will cancel out. This will become 2 root 2. The root 2 will come in the numerator. So that will become 2 root 2 minus pi upon 4. And that will be our final answer. In question number 8, we have to express the function in partial fractions. Now, in the first step, we should know how to write this as in partial fractions. If you do not understand the basics, I would suggest you go into the description, and we have shared the link where all the explanations have been uh, put up for the basics of each chapter. So this will be written as a upon 3x plus 2 plus bx plus c upon x square plus 5. And on the left hand side, we'll have 5x square minus 7x plus 4. Now, when we take the LCM, a will multiply by x square plus 5, and bx plus c will multiply by 3x plus 2. And we'll now compare it with the left hand side. But before comparing, we'll expand it. So when we expand, we'll get ax square plus 5a plus this will become bx into 3x is 3bx squared plus 2bx plus 3cx plus 2c. Now for the x squared terms, we have a over here and 3b over here. So we can say a plus 3b, that will be equals to 5. The x term is 2b and 3c. So 2b plus 3c is equals to -7. And the constant term is 5a and 2c. So 5a plus 2c is equals to 4. Now, as we have three equations, we can make A, B, or C subject from one of the equations and then substitute it into the other equation. We can start off with any of the values. I will start off with A is equals to 5 minus 3B. So when I substitute A is equals to 5 minus 3B, this will become 5 into 5 minus 3B plus 2C is equals to 4. Simplifying this, I will get 25 minus 15B plus 2C equals to 4. So one of the equations will be minus 15B plus 2C. 4 minus 25 is minus 21. And the other equation was, so this was the second equation, this was the one we used, and this was the one from which we got the substitution. So now we have the two equations. We will have 2B plus 3C is equals to -7. Now we can multiply this equation by 3 and this by 2. So we'll get minus 45b plus 6c is equals to minus 63. This will become 4b plus 6c is equals to minus 14. So we can change the sign. This will become minus, minus, and plus. This will cancel out. So minus 45b minus 4b, that is minus 49b. And minus 63 plus 14 will be minus 49. So the value of b will be positive 1. Once we have the value of b, we can easily now find the values of a, b, and c. So as we know that a is equals to 5 minus 3b, so 5 minus 3 into 1 So the value of A will be 2. And 2b plus 3c is equals to -7. We can use any equation. So 2b will become 2 as the value of b is 1. So we can write it as 2 plus 3c is equals to -7. 3c will be is equals to -9, and the value of c will become -3. So now we have the partial fractions. We can write a final answer as a is 2. So 2 upon 3x plus 2 plus b is 1. So bx will become x minus 3 upon c value is -3 upon x square plus 5. Now in the next part it says, hence obtain the expansion of f of x in ascending powers of x up to and including the term in x square. So to expand it, we'll use our partial fraction form, which is 2 upon 3x plus 2. And as we have to expand it, we'll bring these in the numerator. So we can write it as 2 into 3x plus 2 plus x minus 3 into x square plus 5. Now the way to expand it is that we will make sure that we have a 1 over here. So this will become -1 and this will also become power -1. So if we take 2 common over here, we'll get 2 to the power -1 common, and we can write this as 1 plus 3x upon 2 to the power of -1 plus x minus 3 into, if we take 5 common, so that will become 5 power -1, and this will become 1 plus x square upon 5 to the power of -1. Let's expand each of these terms first separately. So expanding 1 plus 3x upon 2 to the power of -1, and we have to get terms up till x square. So the formula is, let's write the formula as well over here. 1 plus nc1, which is n, into b power 1 plus nc2, which is n into n minus 1 upon 2 into b squared. And we'll not go any further as we just need the term till x squared. So we'll get 1 plus n is -1 into b is 3x upon 2 plus, so -1 into -2, that will become 2, positive 2 upon 2 into b squared, that will become 3x upon 2 whole squared. Simplifying this, we'll get 1 minus 3x upon 2, and 2 and 2 will cancel. So this will become 9 upon 4x squared, because this is whole square. So this will become plus 9 upon 4x squared. Now expanding 1 plus x square upon 5, we'll get, so 1 plus, let's use a different color over here. Okay. So 1 plus x square upon 5 to the power of -1. So this will become 1 plus again -1, and in place of b we'll have x square upon 5 plus nc2, that will become again -1 into -2, that is 2 into b squared. So b squared will become x square upon 5 to the power whole square. But now as we can see that x square into square will become x power 4. So we don't have to expand it any further, and we can leave it up till 1 minus x squared upon 5. So we have the expansion of both of these terms. Now we can substitute it over here. And this is 2 into 2 power -1 will become 1. So in place of 1 plus 3x upon 2, we can write 1 minus 3x upon 2 plus 9 upon 4x squared, and then plus, this is x minus 3 upon 5, so we can write x minus 3 upon 5, and the expansion is 1 minus x squared upon 5. We'll have to expand this term first. We can leave the 5 outside over here for the time being. So if you just write it as 1 upon 5, this will become x, and this will become x into x will become x cubed, so we can ignore this term as well. And then -3 into 1 will become -3 plus 3x square upon 5. So multiplying by 1 upon 5, we'll get 1 upon 5x minus 3 upon 5, and then this will become plus uh, 3x square upon 25. So we have these terms over here. Now all we have to do is just simplify them. So 1 minus 3 upon 5, that becomes, so 5 minus 3 is 2, so that becomes 2 upon 5. The x square, the x term is minus 3 upon x and plus 1 upon 5x. So minus 3 upon 2 plus 1 upon 5, the LCM will be 10. This will multiply by 5, this will multiply by 2. So minus 15 plus 2 will become minus 13. So this will become minus 13 upon 10x. And finally, 9 upon 4 plus 3 upon 25. We can use our calculators as well, but the LCM is 100. So this will multiply by 25. This will multiply by 4. 9 into 25 is 225. And this is 3 4s are 12. So this will become plus 237 upon 100 x squared. It is better that we show every single step if you want to avoid any mistakes, because these questions are quite lengthy. So make sure you do all of these working separately to avoid any error, because we cannot do these calculations of NC1, NC2 in our calculators. We have to do all of these calculations manually. In question 9, it says relative to the origin, the point A has position vector as given. The line L has the equation. We have to find the position vector of the foot of the perpendicular from A to line L. Hence, find the position vector of the reflection of A in line L. So first of all, we have to find the position vector of the foot of the perpendicular. So let's say this is A, and let's say this is line L over here. So this will be the foot of the perpendicular over here. We can say this point is X, and we have to find this coordinate. Now, and this will be perpendicular. Now, what we know is that if two lines are perpendicular to each other, we know that their product, the scalar product is equals to 0. The formula that we use is A dot B is equals to A B cos theta to find the angle. And if the angle is 90, cos 90 is 0. So A dot B is equals to 0. But for that, we'll need the direction vectors of both of these lines. Now, for the line over here, we already have the direction vector, which is 3i minus j plus 2k. But we do not know the direction vector for the line AX. What we will do, and what we have to do in every single question like this is, first of all, what we know is that X lies on the line. So if X lies on this line, the equation of the line is 9 minus 1 and 8 plus mu into 3 minus 1 and 2. We can write it as 9 plus 3 mu minus 1 minus mu and 8 plus 2 mu. Now, every single point on this line will have this coordinate, but with a different value of mu. For x, we don't know the mu value, but we can just take our coordinate of x as, so the OX coordinate will be 9 plus 3 mu minus 1 minus mu and 8 plus 2 mu. So if we have to find the direction vector of AX, we know that AX is x minus A. So x minus A will become, this will be 9 plus 3 mu minus 1 minus mu and 8 plus 2 mu, and minus the coordinates of A are 1, 2 and 4. 1, 2 and 4. So 9 minus 1 is 8. That becomes 8 plus 3 mu. Minus 1 minus 2 is minus 3. And 8 minus 4 is 4 plus 8 mu. So now we have the direction vector of AX, which is in terms of mu. So we'll now substitute this into this formula A dot B. We already have the direction of the line, which is 3 minus 1 and 2. So 3 minus 1 and 2. And when we multiply it with the direction vector of AX, that is 8 plus 3 mu minus 3 minus mu and 4 plus 8 mu. And that will be is equals to 0. So when we expand it and multiply first, that will become 8 is a 24 plus 9 mu. And then minus 3 into minus 1 is plus 3 plus mu. And then plus 8 plus 16 mu. Finding the value of mu, 9 plus 1 is 10. And then 10 plus 16 is 26 mu. And we'll take this on the right hand side, 9, 8 and 3. So that will become 24 plus 3, 27 plus 8, which is 35. The value of mu is minus 35 over 26. Okay, so there is a problem with mu. All right, fine. We have the problem over here. This is 8 minus 4 is 4. So this should have been 4 plus 2 mu. So this becomes 4 plus 2 mu. And this will also be 2 mu over here. So this will also become 2. So we'll have 9 plus 2 to the 4. So this will be is equals to 4 over here. So 9 plus 1, 10, 10 plus 1, that will become 14. And then 35 divided by 14 will become, so this is minus 35 upon 14, that is equals to minus 5 upon 2. Now to find the value of x, we can now substitute this value in the direction of OX. So OX will be is equals to 9 plus 3 times minus 5 upon 2, and then minus 1 minus 5 upon 2, and 8 plus 2 into minus 5 upon 2. So this will become 9 minus 15 upon 2. So 9 to the 18. So that will become 18 minus 15 upon 2, which is 3 upon 2. So what we have now, these will be the coordinates of OX. Minus 1 plus 5 upon 2, that will become minus 2 plus 5 is 3. So that will become 3 upon 2. And 8, this minus 5 will become 3. So the coordinates of OX, we can write it as 3 upon 2i plus 3 upon 2j plus 3k. Now in the next part, it says you also have to find the position vector of the reflection of A in the line L. So the reflection of A will be exactly over here. We can write it as A dash. Now what we know is that this A dash, X will be the midpoint of A and A dash. And we already have the coordinates of X. So the midpoint coordinates are, we don't have enough space. So the midpoint coordinates are 3 upon 2. The X coordinate, the Y coordinate is also 3 upon 2, and the Z coordinate is 3. Now to find the midpoint, we can write this as X, Y, and Z over here. And A coordinates are 1, 2, and 4. 1, 2, and 4. So 1 plus X upon 2. So this will become 1 plus X upon 2, comma, this will become 2 plus Y upon 2. And we're just simply using the midpoint formula, and 4 plus Z upon 2. Now solving each of these equations, this is X, Y, and Z. So 3 upon 2 is equals to 1 plus X upon 2, 2 and 2 cancel. So X will be is equals to 2. Then over here we have 3 upon 2 is equals to 2 plus Y upon 2. So that when we cancel this out, 2 and 2 will cancel. 3 minus 2 will be 1. So Y will be is equals to 1. And 3 is equals to 4 plus Z upon 2. So this will become 3 to the 6. 6 minus 4 is 2. So the value of Z will be 2. So the coordinate of the point of reflection of A will be, we can write it as 2i in vector form. That will become 2i plus j plus 2k.